Welcome to this part 2 of the recording for chapter 39. This part deals mainly with the problems from the book. So this is a problem solving session basically. So the problems I am going to consider in here, hopefully they will help reinforce the ideas covered in the lecture, are problem 60. Again, I'm using the 15th edition. If you guys cannot find them in the 14th edition, please let me know if you're using the 14th edition. So problem is 60. Problem 62, and then I'm going to combine problem 70 and 71 because they're really extension of one another. So that's really what this the same idea, except one of them is for a proton and the other one is for the electron. And then finally, the last problem we're going to be that's the last problem is going to be on is basically a data problem. And you know how much, guys, I like data problems because that's basically where physicists now astronomers actually do a lot of work. So problem 60. Problem 60 basically says the following. You have a beam of 40 electron volt electrons. So that's their kinetic energy actually traveling in the x direction, passes through a slit that is parallel to the y-axis and 5 micrometer wide. So we know the A is equal to 5 micrometers for the slit. So this is basically the slit, and then they're traveling with this certain kinetic energy, and the distance between usually the slit and the screen is labeled r. R is actually given to be 2.5 meters. So the diffraction pattern is recorded on a screen 2.5 meters from the slit. So r is equal to 2.5 meters. If it were not electrons, this is identical to what you guys did in optics. So this is not really a difference problem from basically the diffraction from a single slit experiment with optics from Mr. Young. Anyway, the diffraction pattern is recorded on a screen 2.5 meters away. Don't forget that we have the energy in here of this beam of electrons. It's 40 electron volts, and that was given to us. That's how they are fast traveling through the screen, going from one end to the other. What is the de Broglie wavelength of the electrons? Okay. Remember, we have the kinetic energy in here. I'm going to use the classical mechanics because you will see shortly why. We're going to calculate the velocity, and it turns out to be not that big. So the kinetic energy p squared over 2m, and that is my kinetic energy. From here I have an expression for the momentum. So we need the momentum because we want to find the wavelength, and the wavelength is h over the momentum by de Broglie assumption. So again, we need the momentum. So it's going to be the square root of 2m times ke. We have to be careful in here since the energy is given in electron volt. We have to convert to joules, otherwise the units for the momentum are not correct. So if I plug in that into the expression for the wavelength is going to be simply h over square root of 2m, the kinetic energy properly converted. M is for the electrons, of course. So this is, if I plug in all the numbers, this is 6.626 10 to the negative 34 divided by the square root of 2 times the mass of the electron, which is 9.1 times 10 to the negative 31 kilogram, times the kinetic energy, and the kinetic energy is given 40 electrons, and each electron volt is 1.602 times 10 to the negative 19. The whole thing is under the square root. Okay, order of magnitude. This wavelength better be not too long, okay, otherwise we have a problem in here. Okay. First of all, 19 plus 31, that's 50, but under the square root becomes 10 to the negative 25. So in the denominator I have 10 to the negative 25. And I'm left with all of the other stuff, which is 2 times 9, that's 10, times 8, that's 160, times 1.6, which is about 200. Square root of 200 is about 14 if you really want to make it. No, it's about 14, okay? So I'm going to write it about 14 times that number. So you guys are responsible for carrying exact calculations. Mainly, put this in the calculator. 6.626 times 10 to the negative 34. And 6 divided... First of all, I need to put this one as 1.4 and move the decimal point in here, because it was 14. So negative 34 minus 24, that is negative 10. Okay, that's good. So this is 10 to the negative 10 because we wanted distances, not the wavelength, not to be too long. I mean, it's going to be ridiculous if it's of the order of a meter. So this is of the order of an angstrom. 6.6 divided 1.4, it's roughly what? About 4? Okay. So the answer is about 4, 10 to the negative 4, basically for the wavelength. Okay. So this is the wavelength of the electrons. And then, because the slit is of the order of a micrometer. I think, did I get the numbers correct, or do I need to really plug it into a calculator in here to see how this thinks? Let me try to pull the calculator in here quickly to see if this expression is correct in here. I'm trying to find mathematics. I don't have Mathematica installed on this computer. Wow, looks like I have the wrong answer. It's not the proper order of magnitude. So I really need to plug in these numbers in here. Okay, let me see in here. Okay, let me check quickly in here. So what we have, 6.626 times 10 to the power negative. Oh, I forgot to do the square root. Did I? No, probably I did. I don't know. Let's see here. 10 to the negative. Again, it's your responsibility, guys, to make sure that the numbers are correct. That's h divided by square root. That's important. It's a square root of 2 times the mass of the electron, because these are electrons, 10 to the negative 31. Roughly, they're about 10 to the negative 30. And times the energy in joules, which is 40 joules, times the not in joules, actually the energy right now is 40 electron volt, and each electron volt is 1.602 times 10 to the negative 19. Okay, and let's see what this can. Yeah, it's correct, 1.94. Actually, I overestimated way back this number, so it's roughly 2. Actually, it turns out. And the order is proper, so it's 10 to the negative 10 meters. Okay, so that's good. So we have the wavelength of this, guys. How much time does it take for the electron to travel from the slit to the screen? We need to find the time from the one end to the other. So we know the distance. We really need to find the velocity, and the velocity is actually expressed this way. Did we ever find the momentum? We did not. So we have to probably find the momentum and divide it by the. So the momentum is mv. And we found it to be square root of 2m times the kinetic energy from the above expression. Okay. In other words, alternatively, the velocity is simply equal to square root of 2 times the kinetic energy divided by the mass of the electron. And this is the square root again of 2 times 40 times 1.6, because again the energy this is 1.602 10 to the negative 19, to be more specific, 9.1 10 to the negative 31. That's what we have to be careful with, because now we're talking about velocity. Are we justified at all to use classical mechanics and not actually relativity? Because if the velocity that we get from answer is too big, then we have a problem. Then we have to reconsider our solution. So the velocity in here is going to be square root again. So I'm going to put it in the calculator. Hopefully you guys are following this whole analysis in here on your own. Square root of, open parentheses, actually, oops, I have to type it again, SQRT. I'm using, by the way, Microsoft Mathematics, okay? I don't have Mathematica on this computer. I have it on my laptop. 1.602 times 10 to the negative 19. Okay? Divided by, open parentheses, 9.1 10 to the negative 19, 10 to the negative 31, I'm sorry. Okay, and close the parentheses, and that is actually the velocity. The velocity turned out to be 3,752,801, and that is too much, of course. The sig figs in this problem are just 2. So it's going to be 3.8 10 to the power 6 meters per second. Yes, this is a lot less than 300 million meters per second. So it's 1% actually of the speed of light. So we're justified to use the classical mechanics. So that's one thing. Now we need to find the time. The time, we have the velocity, we have the distance. So the time simply is going to be r over v, and r is how much? 2.5 meters? 2.5 meters divided by this speed, which is 3.8, 10 to the power 6. And that is going to be something of the order of 10 to the negative 7, because the denominator is less than the numerator. So again, 2.5 divided by 3.8, and I'm going to pick up, it's going to be 6.57, 6.6, 10 to the negative 7 seconds, okay? Or what is that? 66 microseconds, okay? No, is it 66 or is it 0.66? I'm sorry, it's 0.66. Sorry. Okay, you guys need to be careful with these things in here. We have to move the decimal this way if we want to. Okay, if you're not happy with it, just leave it as is, okay? 6.6, 10 to the negative 7 seconds. So that's how much the time it takes to go from the slit to the screen. Okay, it says use the width of the central diffraction pattern to calculate the uncertainty in the y component of the momentum of an electron just after it has passed through the slit. Oh man, so here is the deal. We have an electron. Okay, it goes through this slit of 5 micrometers. Okay. And then the distance traveled is r, 2.5 meters, and here it's going to impact somewhere on the screen. Okay, we know that this distance in here, this distance is governed by basically the ratio of this distance, which I'm going to call d now. So d over r is going to be my sine, or tangent of theta to be more specific, and tangent of theta for small theta is equal to sine of theta, which is roughly tangent of theta. Okay, actually it's d over r is tangent of theta, which is roughly equal to sine theta. Because I'm going to use the diffraction for this one in here, since it's a single slit, a sine theta is where I find the width of this central, basically bright spot, where if it was light, it's going to be light. Now it's going to be electrons, of course. So a sine theta is equal to lambda. That is actually the wavelength that we measured earlier. Okay, and a is the opening in here, okay? And sine theta, it can be measured from this width of this beam in here in the y direction. So 2d actually is going to be actual width in here. So the width in here is going to be 2d. So I'm going to call the width in here is going to be 2d, and from that expression it's r sine theta times 2, of course, and sine theta, which is roughly tangent of theta. That's why I'm using this expression, and theta from this expression is just lambda over a, or it's sine at least. So the width is going to be simply equal to 2r times lambda over a. So this is basically the width in the, oops, the book is about to fall for me. So this is the width of the rays as they pass through the through this opening. Okay, now this is actually, I can cover this width by assuming now that there is an uncertainty in the velocity of the wave, because initially the wave is actually in the, not the wave, actually the electrons are moving in the x direction, but now for them to reach this width they have to actually have a component of the velocity in the y direction. So this component of the velocity is the uncertainty that was built in here for their motion, because of the fact that they have a momentum that is somehow spread in here because of the uncertainty, the Heisenberg principle. So what we're going to say in this case is that this width is actually equal to the velocity with which they're traveling, but in the y component of it times the time t. Okay, from here obviously we can find this velocity, which is simply in the y direction, which is simply equal to 2r lambda divided by a times the time t. Okay, and the time t is what we measured earlier. Okay, So this is the time basically for which to cover this distance, okay? More or less this entire distance, not just the upper end of it, because that's where the electrons are going to be. So there is this uncertainty plus or minus that value, so that's what gives me delta Vy. Anyway, from here we can find basically, if I multiply by the mass of this expression of the electrons, we're going to find the uncertainty in the momentum. So this is basically what we're saying. The momentum as a value, initially we're supposed to have zero value because we think the momentum is in the x direction, but now because of this refraction we know that the momentum actually has a component in the y direction, and this is its value, 2m times r times lambda divided by the opening of the slit times the time it takes for the whole thing. So if we sub in the values in here, we're going to find delta Py. Okay, so by the way, this has the proper units. This is a kilogram, this is meter, and this is meter cancelled by itself. This is another meter divided by second. So this is kilogram meter per second, which should be a momentum. So delta Py is going to be 2 times the mass of the electron, 9.1, 10 to the negative 31 kilograms, times r, which is 2.5 meters, times lambda, and lambda we find it to be something 10 to the power 10, negative 10, which is about 2 times 10 to the negative 10. So I'm just going to put the estimates in here, divided by A, and A is 5 micrometer. Is that A? How much? Yeah, it's 5 micrometers, so it's 5 times 10 to the negative 6. That's what was given, times the time, and the time we took for it to go from one end to the other was of the order of 10 to the negative 7 seconds. So it's again 6.6 or 7 times 10 to the negative 7. So I'm rounded up numbers in here big time, so hopefully you guys pick up the 2 times 2.5, that's 5 times 2, that's 10. 10 times 9.1, which is another 10. So I'm just getting the order in here, okay? So delta Py is going to be 2 times 10 times 2.5 times 10, that's 100, times 10 to the negative 41, divided by, again, 5 times 7, no, 35, it's about 40, times 10 to the negative 13. Okay, 100 divided by 40, that's about 2.5, times 10 to the negative 29 or 28 kilogram meter per second. So this is delta Py. Okay, again, this is a rough number. You guys are supposed to come up with the better answers in here by plugging the correct values. The mass of the electron is 9.1, not 10. And this number I think is correct, but this is 1.94. So you're going to get a better answer in there. And this is 6.6. And this is actually given as 5 micrometers. So hopefully you guys will have a better answer for delta Py. Okay, so we found that. And use the result from part C and the Heisenberg uncertainty principle for y to estimate the minimum uncertainty in the y coordinate of the electron just after it passes through. Basically find the delta y. Okay, so we know by Heisenberg principle that delta y times delta Py is going to be greater than or equal to h bar over 2. Okay, well, we know they want the minimum error possible for delta y, I'm sorry, since we are already, so it's going to be minimum equals to this amount, 2 times delta Py. Okay, h bar is h, which is 6.627, 10 to the negative 34, divided by 2 pi, so it's going to be 2 in here, that's from this formula, times the 2 pi, times delta Py, which I roughly estimated to be 2.5 times 10 to the negative 28. Okay, let's find the order of magnitude for this value too. Okay, again, you're supposed to find the correct answers for yourselves in here. So delta y, I have 6.6, 2.5 times 4, that's 10, and times 3. 6.6 divided by 3, that is 2 actually, so roughly it's about 2. And then I have 10 in the denominator, but I have 10 to the negative 34 divided by 10, that's 10 to the negative 6. And I have a 10, another 10, so it's going to be 10 to the negative 7 basically meters. Okay, and that is about 0.2 actually micrometer. Okay, and they tell you compare your result to the width of the slit. The width of the slit was actually given to be 5 micrometers. And this is the error, the minimum error you're going to commit in here. So it's well below the actual slit, so we're fine, okay? So we're fine in the sense that if the opening was bigger than the error, then this thing should be spreading far bigger in terms of the momentum. So this is basically the comparison. It's the proper order of magnitude when it comes to this value. So hopefully you guys understand this problem. If you have any questions, please let me know about it, because like I said, all of discussion problems are important when it comes to exam. Remember, this chapter is part of the next exam. Okay, what's the next problem that we promised we should do? And that would be problem 62. Okay, so this is done. So we need this one, 62. For problem 62, what you have a similar situation, except probably it's so you have electrons go through a single slit of 300 nanometers wide. So the A in this case is 300 nanometer, or 300 times 10 to the negative 9 meters, or if you wish, 3 times 10 to the negative 7 meters. Okay, same thing. So, or 30 micrometers. Okay. But the slit in this case is at a distance 24 centimeters. So R is 0.24 meters. Okay. So that's how far the screen is from the slit. At angles plus or minus 20 degrees from the center of the diffraction grating, no electrons hit the screen, but electrons hit all points closer to the screen. So basically, anywhere in between we have electrons, but at this angle in here of 20 degrees, plus or minus 20, so this is 20 degrees, basically we have electrons everywhere in here, but in here, nothing. So there is nothing in this regions in here, plus or minus 20 degrees. This is minus 20 degrees, by the way. Okay? So the question is, A, how fast were the electrons moving when they went through the slit? Okay, so we need to find lambda. Once we find lambda, we find P, and once we find P, we can find what the velocity is. So basically, find lambda using the expression that this is diffraction grating. Basically, m lambda is equal to I sine theta, A sine theta, except that m is equal to 1, because this is the first occurrence of this dark fringe, if you wish, if you're doing a single slit experiment. So lambda is going to be A, and A is given to be 3 times 10 to the negative 7 times the sine of 20 degrees. Once we have that, we have lambda. And then we use the expression for the momentum for the fact that the electrons are behaving like waves to do all of this scattering. So, to do a single slit, so they are going to be h over lambda. So again, h is 6.626 times 10 to the negative 34 divided by 3 times 10 to the negative 7 times sine of 20 degrees. So basically, think that you have found m in the velocity, the momentum. Once you find the velocity, you basically can express the velocity as just p over m, and from here you have h over lambda m. Remember, these are electrons, so its mass, their mass are well known. 10 to the negative 34 divided by lambda, which is 3 times 10 to the negative 7 times sine of 20 degrees. And in here times also the mass of the electron, 9.1 times 10 to the negative 31. Okay, quick order of magnitude. Sine of theta is less than 1, of course, but we really need a number in here. What is sine of 20 degrees? Because it's going to matter a little bit later on. Sine of 20 degrees is 0.34. Okay, so what the velocity is then is 6.626 10 to the negative 34 divided by 3 times 10 to the negative 7 times 0.34 times 9.1 times 10 to the negative 31. Okay, negative 31 and negative 34, that is negative 3. Negative 3 and negative 7, that is negative 4. Okay, now the velocity, we have to be careful with it, because this is 10 to the power 4, because we don't want any number greater than the speed of light, for one thing. Okay, that's why I'm going to be careful in here and do this calculation quickly on a calculator in here. So it's going to be 6.626, okay, divided by open parentheses, 3 times sine of 30 degrees, 0.34, times 9.1. Okay, and the number is 0.7. So it's really a very tiny velocity, so this is well justified. So 0.709 times 10 to the power 4, or 7,090 meters per second. Okay, because basically that is what this number is. Okay, so it's very 7 kilometers per second. It's a very tiny velocity. It's very insignificant. So there is no justification whatsoever for using relativity in this case. Okay, so we found how fast the electrons before they hit. This is how much they do. What will be the next pair of larger angles at which no electrons hit the screen? Well, we have to solve for second angle, basically, where m is equal to 2. So this angle must be theta now, theta 2. Okay, so again, this is just a typical problem with scattering in this case and the single slit. So we have a sine theta is equal, theta 2 is equal to 2 times lambda, and from this one we're going to find theta 2 as being the arc sine of, what is it, 2 lambda over a. Okay, you have to be careful in here with this business in here, because we found lambda from previous calculation, 3 times 10 to the power negative 7 times sine of theta. So theta 2 is equal to arc sine of 2 times lambda, which is a sine of theta 20 degrees. Okay, and a was equal to, so a doesn't matter in this case, it's going to cancel. Okay, because we're dividing by a, cancel the a with the a, so it's going to be 2 times sine. So let's write it, arc sine of 2 times sine of 20 degrees. That's typical problem, by the way, when you do scattering. Okay, typically when you do scattering with single slit, you're going to end up with the situation with the cancellation of the slit in here. So, and the angle theta 2 turned out to be equal to 43 degrees. Obviously it's going to be plus or minus, because it's going to be also on the top or the bottom. Okay, 43.1 degrees, or 43.2 degrees to be more specific. Okay, you're really careful with the calculation here. Now, if you want to find, is there a third one, which is interesting for these typical problems, is there theta 3, so that theta 3 should be equal to arc sine. Again, there will be a 3 in there, and it's going to cancel everything, but it's going to be 3 sine of 20 degrees. Let's see if that's going to work in here and give me some real number. So first of all, 3 times sine of 20 degrees. If it's more than 1, and it is more than 1, so theta 3 doesn't exist. Theta 3 not real, meaning this is where the only two places where we're going to have no electrons. We're going to have electrons in between this angle and this angle. Of course, there will be far in between in here, because it's the second basically set of them. Here is the first set of them. Here also the same thing in here, up to 43 degrees, and then after that they extend to infinity and they fade away. There will be no third angle. This is again typical problem from scattering. Okay, problem 1771. Hopefully you guys understand these two problems because they're related to one another, so expect stuff like this one to be in the exam. Problem 70 and 71, which are, I'm going to tackle them both at once. Okay, as I said. Okay, and then we close this thing with problem 83. Problem 70 and 71 has the same situation. That's why they are identical. So what they tell you in this case is, and I'm going to read both of them, the radii of atomic nuclei are of the order of 5 times 10 to the negative 5. They're going to 15, basically, I'm going to use R, is 5 times 10 to the negative 15 meters. Okay, that's of the order of a Fermi distance. Okay, Estimate the minimum uncertainty in the momentum of a proton if it is confined within the nucleus. If you look at problem 70, it's the same thing. The radii and numerical is of the order. Estimate the minimum uncertainty in the momentum of an electron if it is confined within a nucleus. It doesn't matter if it is a proton or an electron. The answer is going to be the same, because we know delta P times delta X, or delta R in this situation, is at minimum equals to h bar over 2. Okay, so from here we're going to find the minimum basically error that we're going to commit if we force the electron or the proton to exist inside the nucleus. For the proton there is no problem, but for the electron there will be a problem. We'll discover it soon. So 2 times delta R. So again, h bar is 6.626 times 10 to the negative 34 divided by, first of all I have the 2 from the Heisenberg uncertainty times the 2 pi, because this is h bar, okay, times 5 times 10 to the negative 15. If you plug this in a calculator, again 6.626, I should really do an order of magnitude and let you guys do that, but sometimes it's interesting to find the numbers in here, because without them, 2 times pi times 5 times 10 to the negative 15. We may not proceed. So the answer is, the correct answer in here is, it's going to be equal to 1.05 times 10 to the negative 20 kilogram meter per second. We're using SI. Everything is in SI. Okay? So that isn't the uncertainty in the momentum for both of them, because there is no mass, no nothing involved up to this point. Now take the uncertainty in momentum to obtain an estimate of the magnitude of the momentum. Use the relativistic expression for the energy momentum to obtain an estimate of the kinetic energy. Okay, we have the delta P. Take this uncertainty in momentum to obtain an estimate of the magnitude. What is this in here? So we have the momentum. It's the same question, by the way, for this problem 71. Take this uncertainty in momentum to be an estimate of the magnitude of the momentum. I'm sorry. So we found that one. So now what we're saying is the following. Assume that this is actually the momentum of the particle. Okay, that's P. So P for both cases is roughly this number. Okay, for both particles, kilogram meter per second. Okay, proton or an electron, and use a relativistic relationship between energy and momentum to obtain an estimate of the kinetic energy of a proton confined within a nucleus. That's problem 70, and it's the same question. Use a relationship between the energy and momentum to obtain an estimate of the kinetic energy of an electron. So basically both of them. So we're going to do both of them at once. So this is the momentum for either the proton or the electron. So if we were to find the kinetic energy, it's going to be the square root of the total energy, in this case P squared T squared plus MC squared. The whole thing is squared minus the energy at rest, which is MC squared. Okay, so this is true for both the electron and the proton. So let's look at it for the proton. Problem 70 if you wish. So the momentum, we already have it. It's 1.05 times 10 to the negative 20 times the speed of light, and the speed of light is 3 times 10 to the power 8. The whole thing is squared. The mass of the first of all, the proton is 1.67 times 3 times 10 to the power 8 squared. Of course, I forgot to put the 10 to the negative 27 in there. The whole thing squared under the square root minus the mass of the proton, 1.67 10 to the negative 27, times the speed of light squared, 3 10 to the power 8 squared. So this is for the proton. For the electron, Ke, for the electron, that's problem 71. It's going to be the same expression, 1.05 10 to the power negative 20 times 3 times 10 to the power 8, the whole thing squared, because you square the momentum and you square the speed of light, plus the mass of the electron, which is 9.1 10 to the negative 31, times the speed of light, which is 3.8, 3 times 10 to the power 8, squared, the whole thing squared, again, minus the kinetic energy minus the potential energy minus the rest energy for the electron, which is 9.1 times 10 to the negative 31 times 10 times 3 times 10 to the power 8, the whole thing squared. Okay, plug this in a calculator and let's see what we find for the kinetic energy. Okay, so the kinetic energy for the electron first, for the proton first, I'm sorry, so it's going to be, because I'm going to use the same formula and basically change things around. So it's square root of, open parentheses, so the momentum in this case is from the previous calculation, so I'm going to just copy and paste, so open parentheses because we're going to square that number. So this is the momentum times the speed of light, which is 3 times 10 to the power 8. This is where you have to be careful with the power. Sometimes the whole thing is squared, okay, of course, plus the mass of the proton. Mass of the proton is 1.67 times 10 to the negative 27. And this is times, open parentheses, because we're going to multiply it by the speed of light squared. 3 times 10 to the power 8. The whole thing squared. I mean this one squared first. And then the whole thing is squared because we want to find the... Okay. And now close the whole parentheses from outside. Okay. So this gives me an expression. Okay, let's make sure I didn't forget to close any parentheses. Minus this quantity now without the square, of course. This is mc squared for the proton. So what it gave me in here is 3.3 for the proton. Of an energy that's 3.3 times 10 to the negative 14 joules. It's a good idea to express in electron volt by dividing by 1.6 times 10 to the negative 19. So divide this number by 10 to the power 6 divided by, open parentheses, 1.602 10 to the negative 19 to get it in electron volts, because we know stuff in electron volts. So it's going to be 207,000 basically electron volts. So it's going to be actually rounded up to about 208,000 electron volts. This is for the proton inside the nucleus. That's a big energy, that's true. Okay. So we did this part for the proton. Okay. Express your answer in mega electron volts, so it's about 0.208 mega electron volt. Okay, that they want this to be expressed in terms of compare to the potential energy for an electron in a hydrogen atom. So in the hydrogen atom, if you remember from the lecture, we found that the energy for the potential energy is 13.6 electron volt, whereas this one is 208,000 electron volt. Obviously, the nuclear force, nuclear energy is much greater than the electrostatic energy in this case, because that's actually the electrostatic the electric force that is basically responsible for the stability of the hydrogen atom. Okay, this is for the atomic energy and this is nuclear energy inside the nucleus. Okay, several orders actually. 200,000 versus 13 is too big. So that answers problem. Okay, this shows why the interaction that binds the nucleus together is called the strong nuclear force. That's what the statement in the bottom problem is. So problem 71 continues. So we need to find the answer for the problem 71 too. So we need to find that same kinetic energy, except that for the electron, that is now continuation only for problem 71. So for the kinetic energy for the electron, I'm going to go back into the same expression and change just the mass in here and plug in the mass for the electron. The mass of the electron is 9.1, but instead of 10 to the negative 27, it's actually 10 to the negative 31. That takes care of this first term, and I need to do the same thing for the one that is being subtracted. So this is 9.1 times 10 to the negative 31. And enter. So the number is going to be 3.08 10 to the negative 12. Again, in joules. We really need to divide it by 1.602 10 to the negative divided by 1.602 10 to the negative 19 to get the expression. I forgot to put the power symbol in here, although it's just subtracting, which doesn't make sense. Okay, good. And that gives me the energy in joule, which is 19,243 electron volt. 19.2 mega electron volt. Tremendous amount of kinetic energy for the electron, because it's a lot lighter. That's why it has more kinetic energy. If it were to be confined inside the nucleus, versus just of 208,000 for the proton, which is confined to the nucleus, which is really the nuclear energy for that. So if the electron were to be confined inside the nucleus, this is how much energy it's going to have. Kinetic energy, that is. Energy of motion. Because the problem continues and tells you, compare the energy calculated in part B to the magnitude of the Coulomb potential energy of a proton and electron separated by this much distance. So if it were being held there by a proton, where the protons normally reside, so how much potential energy in terms of electrostatic in this case? Of course, is going to be the potential energy in this case due to electricity is going to be just minus 1 over 4 pi epsilon naught times the product of the two charges. One of them is positive, the other one is negative. That's why I put in there the symbol, divided by the distance, and the distance is clearly that radius, because that's at most the distance between these two charges. So in this case the energy is going to be simply equal to 1 over 4 pi epsilon. Okay, let me plug in the numbers. Okay, so the energy is going to be negative 9 times 10 to the negative 9 to the positive 9, that's 1 over 4 pi epsilon naught. Instead of multiplying by e squared, I'm just going to multiply it by 1.60210 to the negative 19, because I need this expression to be already in electron volts. So the answer is going to be in EV. If I want it in joule, I need to keep the e squared in here. And again, the distance is 510 to the negative 15. So plug in these numbers in here in a calculator. That should give me how much potential energy, how much strength the electron is being held by the proton in that location. So it's going to be 9 times 10 to the power 9, that is the constant for the vacuum, times the charge of the electron 1.602, 10 to the negative 19. Okay, the whole thing is divided, open parentheses, by 5 times 10 to the negative 15. Again, this stuff is from physics 2. Okay, so the energy turned out to be about 200, with a negative sign if you like, 88,000 electron volt, or negative 0.288 mega electron volt. Obviously there is not enough potential energy to retain this electron. It has a kinetic energy of 19.2 mega electron volt and just a potential energy of negative 0.28. So if you add the two, the energy is going to be positive. The total mechanical energy is going to be positive, and the electron will be out of there in no time. That's why the electron cannot stay inside the nucleus if it were to be confined. Okay, so on the basis of your result, could there be electrons within the nucleus? Absolutely not, because of the fact that they would have tremendous amount of kinetic energy that will kick them out of the nucleus. Okay, it is interesting to compare this result to problem, okay, yeah, problem 3970, which is for the electrons with the protons and protons. So that's why we did these two problems together. The last problem I want to consider in here for you guys is problem 83. So let me get the Excel going. So Excel, and because I probably closed it without saving stuff, so it's probably going to ask me to, no, I did not. So let me get Excel going. So for Excel, for this problem, as I hope you guys are looking at some windows in here for the Excel spreadsheet. Okay, so as an amateur astronomer, that's problem 83, the one I were doing now. Okay, you are studying the apparent brightness of stars. You know that the star brightness depends on its distance from the Earth, and also on the fraction of its radiated energy that is in the visible region of the electromagnetic spectrum. That when we look at the sky, that's what we see. But as a first step, you stretch the internet information on the surface temperature and radii of some selected stars so that you can calculate their total radiated power. You find the following. So basically what we have in here, the star, we start with Polaris, and then we have Vega, These are two interesting stars because both of them, they are in the northern sky. One of them happened to be right now where is in our northern side, and one is going to be in the future. Every 22,000 years they move. Antares is a big star also. Okay. And then we have Alpha Centauri. I'm going to call it A Centauri, because I don't want to look up Centauri B, because there is actually in the Centauri system there are at least a binary, maybe 3 stars. Okay, Alpha Centauri, Beta Centauri, or Alpha Centauri A and Alpha Centauri B, and then we have Proxima Centauri, which is also part of the same system. Okay, so these are the 4 stars that we are looking at. We have the surface temp in Kelvin. Actually, it's given to you in Kelvin. So when you Google this stuff, so how much is the Solaris is hotter than Earth, okay? The Sun, I'm sorry. 6,000 Kelvin. The Sun is about 5,500 Kelvin. So and then Vega, which is super hot compared to Polaris and the Sun. Antares, which is a lot cooler, 3,400 Kelvin, which is about half the temperature of the Sun. And Alpha Centauri B is about, it's cooler than the Sun, but it's about the same order of magnitude as the Sun. Now the radii, this is the radius in terms of our Sun. So as if compared to the radius of the Sun. So Polaris is a lot bigger, 46 times larger in terms of radius. Vega is slightly about 2.5 times bigger, almost 3 times bigger actually. Antares is huge compared to the Sun, 883. Actually, it's a giant among the stars. And relatively speaking, Alpha Centauri B is slightly less than the Sun. There is Alpha Centauri A, which is slightly bigger than the Sun in the same system. So these are the 3 stars. So what the question is, the radius is given in units of radius of the Sun. So our Sun R_Sun is equal to 6.96 times, I have to be careful now since we're doing, so I have to do an equal sign in here. Equal sign. 10 to the power 8. We're no longer doing stuff that is. So this is basically meters, okay? So that's about 700,000 kilometers basically for the Sun's radius, okay? The surface temperature is a coefficient that gives the measured photon luminosity of the star. So I'm going to call this one actually a name in here. I'm going to call it RS, because I want to refer to this one in the calculation. So this is RS, okay? Or let's make it clear, okay? So this is our Sun. Changed to RS, stays RS. Okay, doesn't matter. Okay, so we need the radius of the Sun for our calculations. The surface of the Sun is the effective temperature that gives the measured photon luminosity of the photon luminosity is the power emitted in the photon. Which star is in the table has the greatest radiated power? Okay. So again, if we use the formula from basically that the power is dissipated per unit area is equal to alpha, did we use a symbol, or sigma times T to the power 4. We have the temperature now in Kelvin, and we can find the radiated power, okay? So radiated power now, we have to be careful in here because there is a number that's going to be a huge power in here, and we probably will lose sight of which power it is. So the power is going to be radiated by this stars is going to be equal to, I want to see the constant that we've used, okay? So I want to see the constant that we've used for these problems. Remember the constant sigma is 5.67 times 10 to the negative 8. Okay, so let me also refer to that, this constant sigma equals to 5.67, because I want to use it time, I'm sorry, again, equal to 5.67 times 10 to the negative 8. Okay, I want to refer to this number in here as sigma in my calculations. Okay, so we have sigma, and pi, I think Excel uses the word pi for it. So let's find now the power. Okay, so basically we have to multiply sigma by this temperature to the power 4 times, of course, this radius to the power times, of course, 4 pi r squared, the radius of the sphere. So it's going to be equal to, okay, sigma times the area, which is 4, times pi. I think pi is, you need the parentheses for it because it's a function in Excel, times, so sigma times 4 pi times the radius squared, and the radius squared times the radius squared, and the radius squared is equal to 46 in this case, times the radius of the sun, and the radius of the sun is rs, so let's put it rs in the expression. Okay, and of course squared. I'm sorry, I need to open parentheses in here quickly. So when you're writing equations like this one, you have to be careful here. So it's again for 46 times open parentheses times rs, that's the radius of the sun, the whole thing squared, that gives me radius of the sun, sigma times this number times that, times of course the temperature to the power 4 times this number to the power 4. Okay, if we did everything correctly, the formula should be fine, and we get this number. Control C, paste it in here, paste it in here, and paste it in here. So we have how much power is radiated by each one of these formulas. The reason why you name variables when you're doing problem like this one is because when you transfer them to a formula, they stay the same way. So sigma is there and rs is there, so they don't change no matter what you change. In this case, the cells only change and reflect the cells that you move on. So this is a good technique to use when you're solving with Excel to change the to use the change variable. So we have the radii. Which star in the table has the greatest radiated power? Obviously, if you look at the table, look at just at the powers. You have 10 to the power 29, 10 to the power 28, and 10 to the power 31. That would be Enchantress, although it's a lot cooler, but it's being giant, so it radiates the most power. Albeit it's at a lower temperature, not as hot as, for example, Vega, which is super hot among this bunch, but it radiates far more energy than any of the others, okay, because it has a huge area. Okay, so that answers that. For which of the stars, if any, is the peak wavelength lambda m is visible in the range between 380 and 700 nanometers? So we need to find the peak frequency in here, okay? Again, there is another formula that involves 2.9 10 to the power -3 as a constant. So we need to find that constant, and we call that constant, let's call it alpha, okay? In here, so alpha is 2.9 equal 2.9 times 10 to the power -3. Okay, because we will need this formula since we have the temperature in Kelvin, so we need to find the wavelength max, lambda max. Okay, so again, just this alpha, the expression that we use in this case, it's this alpha divided by t. So again, equals to this number. Oh, I didn't label that one. I need to give it the name. So this is alpha, so that we don't have to worry about that too, because if we transpose it, the next numbers are all going to be 0. So this is going to be equal to alpha divided by the temperature. So Control C, Control V, Control V, and Control V. Now I want to find the range because they tell me specifically the range is between 380 nanometers and 750 nanometers. So I'm going to multiply this already by, or multiply it or divide it actually by another number, which is a nanometer, which is 10 to the -9. Okay, so it's going to be open parentheses 10 to the -9, and all the answers now are going to be in nanometer actually if I do it this way. So now I know exactly where this number is. So this is 482 So let's paste it first of all. Okay. Is Polaris in the visible range? Okay, the peak frequency, that is 480, is yes within this range. So Polaris is yes. Okay, Vega 302 is no. It's actually, the peak frequency is actually in a very, very short wavelength, meaning it's super hot. It's actually, it's in the UV range, ultraviolet range, and that our eyes cannot detect. Is Antares in the visible range? Not either. That is actually in the infrared. That's where it peaks. It doesn't peak in the visible range. You can all see all of these stars, but we're talking about their peak frequencies, whether or not you can see them or not. Alpha Centauri actually is just smack in the middle, probably in the range, which puts it right around the color of our sun. Okay, so it's actually a little cooler than the sun, so it appears a little less white. So it's more probably of a greenish. The green cannot, because the green is just smack in the middle, so it's probably yellowish star. The sun is actually white. Okay. So this is basically the stars. So two of them, Polaris and Alpha Centauri B, they appear in the visible range. Their peak frequencies appear in the visible range because it's between 380 nanometers and 750 nanometers, whereas the other two, Vega is in the UV region and Antares is actually peaks in the infrared region. Okay, it's above the 750 nanometer. The sun has a total radiated power of 3.85 10 to the power 26 watts. Okay. Which of the stars, if any, have a total radiated power less than that of our sun? Okay, so it's just a matter of now comparing that one. Obviously, if you can clearly see from these numbers, it looks like these two have less than the sun in terms of radiated power. Okay, I'm sorry, did I say that? It's only this one. It's only Alpha Centauri B is slightly less than the sun. It's a little cooler and less in size, so that's why it's less. The others have more. In other words, just take that ratio for the power of the sun, so P hour of the sun, and that is equal to, according to this formula, this number is 3.85 equal to 3.85 times 10 to the positive, actually, open parentheses, I don't know if Excel groups or not, so power 26. Okay, so this is how much the sun radiates in terms of energy. Obviously this big number. We're going to give this one a name, so we're going to call this guy PS, or power sun, P sun. Okay, so now we're going to find the relative power. So all we have to do is take this power that we found earlier equals to this power that we found earlier and divided by the power of the sun, P sun. Oops, P sun, not PS. Sorry. Okay, so we're in business. Now compare this one, paste it in here, and all of the other four, and which one is less than that of the sun? Obviously this one is. So Alpha Centauri, yes. Everybody else radiate more than the sun. No, no, and no. So you have basically done an analysis without graphing, without doing any plotting, without doing anything in here. Okay, but the point being in here is you use Excel to help you solve with a lot of these things without doing a lot of work for solving this problem. If you have an exam where you have problems like this ones with data and things like that, I expect you guys to have been a little bit proficient to not waste a lot of time doing calculations like this one, basically trying to arrive at answers for your problems. Okay, I hope I was thorough in these problems. If you guys have any questions about how these problems went, or questions and things like that, please let me know. The next chapter, which is chapter 40, we're going to introduce a better mechanics to explain what's going on with the hydrogen atom, and actually explain what's going on with all of the atoms, including later on molecules and even solids and everything that we know today. Probably the most precise theory that physicists have ever come up with, which is quantum mechanics. Thank you.